Hello friends, so in the last video we have discussed about the rules of Rauthovitz criteria. In this video we'll be solving 2 or 3 peculiar examples about how to deal with Rauthovitz criteria in some special cases. So let us take a transfer function and let's start. Suppose the transfer function is s cube plus s plus 2. This is not a transfer function, sorry, this is my characteristic equation. That is s cube plus s plus 2 equal to 0. So let's start off with the Rauthovitz criteria. That is, how many rows will be there? 4, right? S cube, s square, s to the power 1, s to the power 0. What will be the first row? It will be s cube, s square left s1, that is 1, 1. Now s square, there is nothing absolutely, right? And s 0, that is 0. Now we are stuck in a peculiar problem. The problem is that we have a 0 out here. So whatever we do, we have to divide it by 0 and that becomes infinity. So that's a huge troublesome scenario. So what to do in such a case? That is, in such a case, if we get only the first digit of a Routh array as 0, then we need to consider this as epsilon, where epsilon is very small, and we need to go on with the calculation. Let's go on with the calculation and see what happens. So this is epsilon minus 2 by epsilon. So this is epsilon minus 2 by epsilon, right? This is 0 and this is 2, right? Now you need to consider this. Epsilon is very small, so neglect this. So this almost equal to minus 2 by epsilon. So this almost tends to minus infinity, right? Epsilon minus 2 by epsilon, this is neglected, is almost equal to minus 2 by epsilon is almost equal to minus infinity. So there is a sign change out here. So this is a positive, positive, negative, positive. So there are two sign changes again. So there are two poles on the right half of the S plane. Did you get it or not? As there are two poles on the right half of this S plane, we can say that the system is not stable. Right? This is one such peculiar example of where if we get the first digit of any row as 0, then we have to consider it as epsilon and go on. If we get another row again as 0, then we need to consider it as epsilon 1 or epsilon 2 and go on with the problem. Now let us discuss another problem. Okay, so the next problem, let us take another transfer function. Another characteristic equation. 2s to the power 4 plus 12s square plus 16 equals 0. Let's make it. So how many rows would be there? 5 s to the power 4 s cube s square s to the power 1 s to the power 0. It will be direct to 12 and 16, right? There will be absolutely nothing else out here, right? There will be absolutely nothing else. So this will be 0, 0 and 0 row. So how to predict that whether this system will be stable or not? This system, what we have to do is, if we get a whole row as 0, then what we need to do is we need to consider the previous row, that is this, and we need to differentiate the values of that row. That is, we need to differentiate 2s to the power 4 plus 12s square plus 16, and the coefficients that we get, we need to put it in this equation and check whether, and then go on with the calculation, right? So if we go on with this calculation, we can easily check that it will be, if we differentiate this, then it will be 8s cubed plus 24s is equal to 0, right? Nothing else. So we'll put it as 8s cubed plus 24s plus 0. Now let's go on to calculation. 8 into 12 becomes 96 minus 48. And 48 by 8, that becomes equal to 6. This would be 16 minus 0 by 8, that is 16 again. going with this is obviously greater. This is 6 first 24 into 12, 144 minus of, yes, so 16 to 8 is 128, so 144 minus 128, that's equal to 16 by 6, 16 by 6, and the last place is definitely equal to 16 by 6. By this it's 16, right? So we can find that this whole row, there is no sign change. I was not paying attention much to find out these values because just we want to know whether these values are positive or negative. If it is negative, then there's a sign change. If it is not, there is no sign change. So here these are positive values, so there is no sign change. So the system is stable, right? So we can find out that whether a system is stable or not by just doing these simple calculations. That is, if we see that the system has just the first initial value as 0, then we can calculate it as epsilon. We can take it as epsilon and then go on with the calculation, find whether the system is stable or not. Or if the whole row is 0, then you know what to do. Then the previous row, this is known as the auxiliary equation. We need to differentiate the auxiliary equation and then put the value of the auxiliary equation, differentiation coefficients, and then say that what my values would be. Now there is one thing that we need to keep in mind. If a whole row is 0 and we have done this auxiliary equation case, then the system is stable, but there will be two poles on the imaginary axis. Now we need to find out the two poles on the imaginary axis. That's very simple to find out. What we need to do is we need to just check the roots of this equation, right? We need to just check the roots of this equation, that is 2s to the power 4 plus 2s square plus 16 plus 12s square plus 16. Let's do so and find out what the roots are. Now 2s to the power 4 plus 12s square plus 16. Let's take s square as x, so this becomes 2x square plus 12x plus 16. We're going on that becomes my s to the power x to the x square plus 6x plus 8, that's equal to 0. That's quite nice, right? So x square plus 4x plus 2x plus 8 equal to 0, or we get that x plus 2 into x plus 4 equals 0, right? So this gives me s square equal to minus 2 and s square equal to minus 4, right? So this gives me s equal to plus minus 2j, plus minus root 2j. This gives me s equal to plus minus root 4j, that is equal to plus minus 2j. As we had thought that there are poles on the imaginary axis. Now we get these 4 poles on the imaginary axis. Now we need to find out the fundamental frequency. That is, this system will have poles out here, right, and other poles maybe out here. So we need to find out what the fundamental frequency of the system is. The fundamental frequency is determined by the lowest, that is the closest pole. That is, here it is root 2j. So the fundamental frequency would be omega equal to root 2, right? So that is how we can find out the fundamental frequency of any system. Thank you for watching.